So this is a video that introduces work. Work is a scientific term used to describe the action of a force which moves an object. When a constant force F is applied to move an object some distance d, the amount of work performed is W equals F times d. Okay? So if an object moves along a straight line with position function s of t, then the force F on the object in the same direction is given by Newton's second law of motion, which is mass times acceleration. Okay, so this is force is equal to mass times acceleration. And so force is in newtons. So the newtons are kilograms per meter squared, or meter per second squared. So mass is measured in kilograms, kg. Now, something we need to be aware of is the conversion of kilograms. Okay, so make sure you know how to convert between kilograms and grams and so on, right? So if I went in and said, okay, kilograms to grams, there's 1,000 grams is a kilogram. Okay, so you need to be able to convert, right? This is equal to 1,000 grams. All right, whatever those conversions are, you need to make sure it's kilograms per meter squared, right? And if they tell you like centimeters, then how many centimeters are in a meter? There's 100 centimeters in 1 meter, I think. So let's make sure. Meters to centimeters. Yep. And so you just need to make sure that you're converting correctly. All right. Now, acceleration is going to be the second derivative of the position function. So that's my position function is s of t. So the second derivative of s with respect to time, t, and that is where the meters per second squared comes into play, because I'm taking the derivative with respect to seconds. So meters over seconds squared, because it's the second derivative. So that's why there's that squared coming in, that dt, right? So what is the definition for work? Work is equal to the force times the distance. All right, so W equals FD. And the work is defined in Newton meters. So a Newton meter, also known as a joule. So in your homework, it's going to have like a blank, and then out to the side, it'll say it'll have like a J there. So your answer needs to be in Newton meters. Okay, Newton meters. Remember, the force is a Newton, so that's kilograms per meter times meters per second squared. And then distance is in meters going on there. So that's a Newton meter for work. And if it's not the metric, then we have F in pounds. Which is LB, and D in feet. Okay, and this is known as foot-pound. And the conversion between foot-pounds and joules, this is equal to 1.36 joules. 1 foot-pound is equal to 1.36 joules. Okay? So that kind of gives you a summary of work here. Things to note: mass and weight are closely related, yet they're different concepts. Okay, what does that mean? So the mass of an object is a quantitative measure of the object's resistance to acceleration, whereas instead of mass, the weight of an object is the measurement of the force applied to the object by the acceleration of gravity. Okay? Since the two measurements are proportional, the weight is equal to the mass times the gravity. Okay? And so they are often used interchangeably in everyday conversation, but when computing work, you must be careful to note which is being referred to. When mass is given, it must be multiplied by the acceleration of gravity. So if all they say is like the mass is equal to 52 or whatever, okay, then you must accelerate by must multiply by the acceleration of gravity. Maybe that's 9.8 meters per second squared, right? In order to get that weight. Okay, so mass times the gravity to get you your weight. All right, so you got to be careful there when you're talking about the difference between mass and weight in the problem. So be careful when you're reading through. Okay, so when a force is constant, the measurement of work is straightforward. Right? Say for example, we want to know like how much work is done by lifting a 1.2 kilogram book off the floor to put it on a desk that is 70 centimeters high. Okay, so I'm going to assume acceleration due to gravity is 9.8 meters per second squared, all right? So how much work is done? Well, to get work, I do the force times the distance. But to get the force, I need to be able to do mass times acceleration, right? Well, the mass, they tell you that the mass of the book is 1.2 kilograms. All right, so remember, force has units of kilograms per meters per second squared, right? Okay, so my force here, the mass 1.2 times the 9.8 assumed acceleration gets me what? It gets me 11.76 newtons. All right, that's my force. Now, what I need to get the work is I need to multiply by the distance. Okay, so work is equal to force, which is 11.76 newtons, times the distance. Okay, distance, remember, force here is newtons, and distance here is meters. So a joule is a Newton meter, right? Now the problem here, this problem has centimeters. So I need to convert to meters. How do I do that? Well, 70 centimeters is equal to 0.7 meters. Okay, there's 100 centimeters in a meter. So this is 0.7 meters. So make sure that your units are correct. If your units aren't correct, that's how you mess up. Multiply this through, you get 8.232 joules, okay? So just be careful. If this would have been in grams, you would have needed to convert it to kilograms. Same thing, it's because you want the end result to be Newton meters, right? For force, kilograms and meters per second squared, that's assumed in right there. So as long as you're in kilograms there, you're good to go for force, and then you push into the next level. All right, so just keep that in mind, that the units actually do matter. Now this is the simple case when force is kept constant, but what if the force is variable? How do you handle something variable? So like a scenario where force is changing, imagine you're like climbing, so you've got some climber pulling a 200-foot rope on some vertical face, okay? So like, you got, somebody, and they're up here at the top and they're pulling up this rope, okay? And it's 200 feet long. Well, guess what? Let me give this person a head, right? Okay. So as you're pulling in this rope, as you're pulling it in, what's happening? Well, you're getting less and less and less rope. Okay. Well, as I pull in less and less, more and more rope, and there's less hanging here, maybe the rest of the rope only weighs like 5 pounds, whereas before, when you had all the rope here, it was like 50 pounds. So it gets easier and easier. The work required to pull the rest of the rope in is decreasing as you pull the rope up. So the work is variable throughout this task. So in order to account for that variable change, that's whenever we take into account Riemann sums and calculus. Okay, so we define the work of a moving object to be equal to the sum from I equal 1 to n some wi, these individual work slices, which a wi would be basically some f of ci times some xi plus 1 minus xi, which is a fancy way of saying a delta x, right? And so what this looks really familiar to is your Riemann sum f of ci delta x. And so to get the exact work, we let f of x be a continuous function on a to b. Okay, and this function is going to describe the amount of force being applied to an object in the direction of travel from distance x equal a to distance x equal b. Okay, the total work done on a to b is w equals the integral from a to b of the force function dx. Okay, so I'm literally integrating the force function from a to b, and that's how we determine the total work performed.